Hello everyone, I want to start by apologizing for being sick and if you hear any construction noises in the background because they're doing construction in my building. So, what I'm going to do is just briefly go through the material for the lecture that you will be missing in person. Thankfully, a lot of the stuff's either computational in nature or kind of a theoretical underpinning for some of the things we'll do later that you can skip out on some of the exact details there. So it's not a super overly critical lecture to miss, but in my opinion, it's a fun one. Okay, so for this question, it says find the Fourier series for the pi periodic version of this function. So the first thing we have to do is figure out what pi periodic version is. So our definition of pi periodic was you take this function and you build it over an interval that has a length of pi and is centered at 0. So in this case, this would be pi over 2, half the length, and this over here would also be pi over 2. Now I have to think what x squared looks like. It looks like this. I'm going to put open circles here. Oops, I'm started with the wrong question. So we're going to put open circles here, just because we don't know what's going to happen there. You could fill those in, but I'll leave them open for reasons later. Now, this function has multiple copies of itself, right? So there's another branch that kind of goes here, and another branch that goes here, and all of these have a length of pi, so this would be 3 pi over 2, etc. So that's what we're looking at. And for Fourier, we're really interested in stuff in the middle, and because the sine and cosine modes that we'll use to expand this have the same period as the thing we care about, the sine and cosine stuff will automatically kind of build these extra things in there. That's the idea of the pi periodic version. So the questions we need to ask: what is tau? What is omega? And what bases of functions should I expand in? So tau is always the length of the interval. So in this case, it's just pi. Omega is always defined to be 2 pi over pi. So in this case, that simplifies to 2. So because of this, the functions we want to work with would be the complex exponentials of 2njt. So typically, we've solved these by using the complex form, but we know this is a real valued function, so the end answer will be real valued. So what we can actually do is we can use our new things with sine and cosine to actually expedite the process of skipping all the things with complex exponentials. Our x squared is even. Since x squared's even, the previous results that we talked about in the last class says that the Fourier series, well, define the squiggly equals soon, is going to be C0 plus the sum from n is equal to 1 to infinity of Cn cos omega, so 2 n t. Right? And here, to find these coefficients, we had the formula that we derived last lecture. C0 is just going to be the average f of x with 1. So that's literally the average of f over that interval. And Cn, for the rest of the values, will be 2. 2 coming from the fact that this goes from 1 to infinity instead of minus 1 to infinity. And symmetry, in the case when I have a real valued function, lets things collapse, so I get a 2 times the inner product of f of x with cosine. 2nx. Alright? So now these, computing these terms, is just a 119 problem from way back when. So we'll set up the intervals, and then we'll tell you what they evaluate to, and when I upload solutions, you will get a copy of the 119 steps, some of the 119 steps there. So here, I want to integrate over the whole domain, minus pi over 2, of f of x, so x squared, times 1 dx. Okay. Now this is pretty straightforward integral, just power rule, knock it out, and you end up, and 1 over the length of the interval, so 1 over pi. Do not forget your 1 over the length of the interval. So when you put all this together, you end up with pi squared over 12. Okay. Now for the next one, 1 over pi times my 2, so 2 over pi. The integral minus pi over 2, x squared cos 2 n x dx. Here you have your options. You can use the integration by parts, or you can do integration by parts with the tabular method. Those are your two general types of options. Here, I'm just going to say 119 goes burr, and we end up with pi n squared minus 2 sine n pi plus 2 pi n cos of n pi all over 2 pi n cubed. Now I stopped at this step to show you how the things simplify with the cosine and the sine. So if I draw the unit circle, right, you think, where does are the angles of n pi? Where are those located? Well, 0, 1, 2 is back here, 3, 4, 5. So it alternates back and forth. So all these ones are the even values of n, and these are the odd ones. Odd. Okay? So if you think about sine is, well, sine over here is 0, right? Sine over here is also 0. So this tells us that this term will simplify to 0. Cosine's the x coordinate, so it changes from even to odd. So I want a function that's 1 here and minus 1 here, and it turns out the function that does that is minus 1 to the n. Yeah. So all this goes away, and I end up with 2 pi n over 2 pi n cubed. That becomes just n squared, and the negative 1 to the n. Okay. Now, throughout this computation here, I didn't have any singularities where there were certain values of n where the integral was evaluated differently, because the Cn, this formula, is only valid for n bigger than 1. Right? So if I put these together, my Fourier series will be this constant term plus the sum with this negative 1 to the n over n squared, put in here with my cosine. Okay, so that really is all there is to it. The hard part you'll find is setting up the 119 stuff, and you might struggle with this, figuring out how these simplify until you kind of get used to it. But once you try a few, it's pretty good. Okay. Let's go back and do this one. Sorry for doing it out of order. I'm very much going to one-shot this because this is quite painful. So here, I want to go pi periodic version of this. So I want an interval of length pi centered at 0, pi over 2, and negative pi over 2. Give me that. Here, I get my 2x, so I'm going to put a big circle here. 2x does this kind of thing, straight line through 0. If I plug in pi over 2, I get pi, so this is up at pi. This is down at minus pi. Right? And this repeats, right? I get circle, 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 yada, yada, yada. Okay, so first thing again, find tau. Tau is always the length of the interval. Tau is pi. Omega. Omega is always 2 pi over tau. Tau is pi, so omega is 2. So it's the same bases we had last time. This is actually for a purpose. We're going to show you a trick in the future by looking at these two examples. Hashtag derivatives, integrals, fun times. From here, we look at f and we think, well, what type of function is f? It's real. So we could do the complex trick, the thing that we did to evaluate the previous Fourier series, or we can use our new results. Since it's real, if it's even, I get a cosine series. If it's odd, I get a sine series. In this case, it's odd, so I get a sine series. So I can say from previous results from last lecture that my function 2x is going to have a sine series. N is equal to 1 to infinity of Sn sine 2nx. Again, 2 coming from omega, and x, that's always there. Now, from here, if I want to compute the coefficients, the formula for Sn is 2 inner product f of x with my sines. So now, 2nx, there we go. So now again, the 2 comes from symmetry, the fact that f is real. Symmetry allows us to simplify things out and make the sum go from 1 to infinity instead of negative infinity to infinity, and gives us the 2. Now here we do the exact same thing we just did, right? We go compute Sn. Sn, not to be confused with eating in German, is going to be 2 divided by the length of the interval, pi, the interval minus pi over 2 to pi over 2 of 2x, that's what f of x was, times sine 2 in x. So you do your integration by parts, either with the tabular method or the standard method. And when you do this, when 119 goes burr, the middle step that you're going to arrive at is 2 sine n pi minus n pi cosine n pi all over pi n squared. Now, again, I'll just do the, oops, don't know why that disappeared. Okay, there we go. I'll just do the same analysis we did last time. Here I got my unit circle. Here's the even ends, here's the odd ends. Sine is always 0. Cosine alternates between -1 and +1, with negative corresponding to even, so -1 to the n. So here, once I simplify this, the pi's cancel. The n cancels with the squared, and I end up with -2 minus 1 to the n over n. And I can simplify this further if I want. I can absorb the negative into the -1 to the n and write it -1 to the n plus 1 over n. Okay, so I take these coefficients, I slap them in here, and I got a Fourier series, right? So again, you might find some of the 119 review to be tricky, just because, I mean, integration is fundamentally harder than differentiation, so that's often a sticking point. And you might find these circle arguments a little tricky. Try a few. They're not too bad once you get used to them. It's really just asking, where is this angle on the unit circle, and is that one of the known angles where I actually know the values, right? So 0, pi over 2, pi over 4, pi over 3, that kind of thing. Okay, so now we're going to go to the fun part of the lecture. We're going to talk about types of convergences. So, with Fourier series, we care about how it converges. For the purpose of engineering, the type of convergence tells us information about how the Fourier series behaves, either when we truncate it, which one often does when working with Fourier series of finite data, right? So it's not going to be a continuous, well, not continuous. You're not going to go up to infinity if you have finite data, that kind of thing. The other thing we care about is the end behavior, right? If the Fourier series converges very nicely, then it tells us some nice things about our signal, and there's some nice engineering applications there. So what we're going to do is we're going to briefly talk about the ideas of the different types of convergences. That's going to be the main focus for today's part of the lecture. And in subsequent lectures, we're going to take these and see what happens in the particular case where everything's Fourier. Yeah? And I'm going to give you a homework question asking you about the kind of more broad convergence, just to make you think about the idea a little bit. But I won't put that on the final exam. I will only put the end results that we'll get in the next lecture when we rederive everything for Fourier. So, yeah, it's good to know this type of material so that you understand what's happening at a bit of a deeper level other than the theorem said this, therefore blah. Yeah. Okay, so in 119, you dealt with convergence of real numbers like this. right? There's really one natural way to define convergence. It does or it doesn't, or yes or no. There are some shenanigans you can do there, but that's the idea, right? But now if I give you a collection of functions, the types of convergence isn't unique, right? So let's draw a nice little picture. So suppose these are my xy axes. Suppose this is a function that things will end up converging to, right? And I can have a sequence of functions. I'm going to make them get stuck at the endpoints for the purpose of the demonstration. Well, actually, we'll put this here. So we'll say this is f of x is the first one. Now I have a sequence of functions. So this one, I could call, oops, let's keep it normal function. I can call this f1. Right, so this is just the first element in the collection of functions, right? I have f1 of x, f2 of x, da 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 da, and I'm asking, like, what does it mean for the limit as n goes to infinity of fn of x t equal f of x, right? What does this mean, right? And it turns out there's not a unique meaning. So here's my f1 in this little picture. We'll pick another color. The wonderful thing of having this online is it's more colorful. So I can pick another guy here. I could call this f2, right? And these are just sample demonstration functions, right? And we'll put one more. So I'm going to pick a point here and what I pick on. So I'll say this one really close here, and I'm going to make it jump up and then jump back down. So this kind of thing here. We'll call this thing my like FK or whatever, right? Okay, so I can ask, like, and I'm also going to take this little curve here and cut a little circle here, and I'm going to put a solid little dot there, right? So a natural question I could ask is, like, does the sequence of curves that I drew here, if I fill in and add an infinite number of curves, which I obviously can't do, does that approach the red thing that goes here nice and smooth, jumps at this point and goes nice and smooth along here, right? And one natural way that you can do it, it's called pointwise convergence, PW for pointwise. This is saying, is it true that no matter what value of x, no matter what number here someone gives you, so in the domain of f, is it true that for those values of x, for that one that you pick, for each individual value, the limit as n goes to infinity of fn of x goes to f of x, right? The idea here is for any value of x, so some random value of x someone picks, these guys approach here, right? This is called pointwise, and in this case, if I kind of keep imagining I draw the blue curve getting closer to the red here with this little peak up here, you could kind of think, like, for each point, right, if I give you, that might be a bad color, but if I give you a point here, well, this limit idea down here just becomes like, what is that distance doing? I'm going to pick a different color, right? What is this distance doing? Is that distance going to 0 for that x? If so, okay, we're good at that point. But then I do it over here. Is that distance going to 0 for that x? Yeah, okay, looks good there. I do it here. Is that distance going to 0? I do it here. Is that distance going, oops, is this distance going to 0? All right, so just ask, for every point, does this act like your Math 119 stuff? All right, now here we're doing it with sequences of functions, but it turns out that if you want to do it with sums, sums are just sequences of functions. All right, so this is the first type of convergence, is it converges pointwise. The next question we can ask is what's called uniform convergence. So for uniform convergence, we're not interested in what happens at a single point. We're interested in what happens everywhere, right? So uniform convergence is defined on an interval. And instead of like, hey, for every x it behaves well, we want it to behave well for all the x's in a very particular way. We want it to be true that the limit as n goes to infinity of the maximum, in mathematics, this is generally replaced with an idea called infimum. We're not going to introduce that because for the purpose of this class, the idea of maximum is sufficient, but the maximum of the difference between this function and the thing it's supposed to converge to would go to 0. Right? So the idea of uniform convergence is stronger than going for each point, right? Because if I go to each point, well, the way that these approach to my f of x doesn't have to force the maximum error to behave well. We have an example right here, right? If I'm trying to converge, like with this nice, smooth curves that I've been drawing, if I want to converge to this discontinuous function, if I go to compute the error, we're going to zoom in just for emphasis, right? If I go to compute the error right next to this dot, right? Right where this jump is, assuming that's a vertical line, right? The error right on this tiny little slice, if this function's continuous, the blue curve needs to be near, right? Needs to be over here near the red dot. And if this is continuous here, this needs to be near that dot. So the error gets close to whatever this length is, right? Near those points, right? And that doesn't go away. The continuity of the two functions imposes that I'm going to get an error that stays basically the height of that jump, right? Literally, it will be the height of the discontinuity of the red function, so whatever that distance is. So here, even though for every single point, right, all along here, my sequence of functions is getting closer to the red line, at this particular point, the maximum error is not going away. It's staying, right? So it's not going to 0. So in this case, the picture I drew, we don't have uniform convergence, right? That's actually why I cut out the hole to demonstrate this, right? So it turns out, big math theorem, uniform convergence preserves continuity. So if I give you a collection of continuous functions and I take their uniform limit, right, if they converge uniformly, the limit will be continuous. And this has ramifications for Fourier, right? We'll talk about that in like in-person lecture with Gibbs phenomena, all that good stuff. Normally I would ask, are we all okay with this? But that's the idea. So point-wise, for every point, it converges. Uniform, the maximum error converges. Those are the two ideas. There's one more that we're going to use. This one's mostly for completion. We can have L2 convergence, or convergence in the mean, also called convergence almost everywhere. So you can talk about error at a point, error maximum, but you can also talk about average error. So I'm just going to give you the definition. And there's slightly different definitions that one can give if you look in literature. I'm going to give you this one because theoretically it works well enough for the stuff we are doing. And I don't want to make things overly complicated since we're not going to do much with this, right? Okay. This guy dx is 0. Okay. So this thing in here is basically our criteria to be in, well, it's the integral that we examine for our criteria to determine if a function is in L2, right? So what this is really computing is it's a type of average of the function, like the L2 mean, if you will. To make it formally the L2 mean, you need some other little 1 over the length square root stuff floating around, but this is sufficient for us, right? So what this is effectively saying is that in some sense, the average between Fn, the sequence, and F goes to 0. So it's really kind of a comment about the area between the two curves, but it's a squared area, so it's kind of a scaled thing, right? So here, through the power of paint, I can just tap, right? So this is really asking, does a very particular weighted average of this black area go to 0, right? So it's not strictly the black area because I square it, right? If I'm bigger than 1, when I square it, it becomes a bigger number. If I'm smaller than 1, when I square it, it becomes smaller. So there's those kind of considerations, but that's the idea, right? What's going on with that little black area? Does that go to 0 in a sufficient way? If so, we say L2 converges. For Fourier, we want L2 because we can say a nice theorem that if I give you a function that satisfies the condition to be in L2, namely, just to put that so I know people will definitely forget it, namely that the integral from, well, if it's in the context of Fourier, minus tau over 2 to tau over 2 of the modulus of f of x squared dx. So if this is true, then we can say that the function will be equal in this sense to its Fourier series. All right, so it's a very nice closure property. It says L2 is enough to have some nice things with Fourier. Okay, so here's the formal definitions. These are the bits that you'll use for your homework, right? So the sequence converges to L2 norm, or converges to the mean, or converges to almost everywhere if this limit goes to 0. Mechanically, if I give you a sequence of functions fn, and I give you a function f, or you find a function f, you plug them in, you integrate, you take the limit. That's it. That's all you have to do to check it. And this is really saying that the average error goes to 0. That's the idea. Pointwise convergence. Here, what you do is you take your fnx, you subtract your f of x, you treat x as like some number, right? Like, don't plug in a number, obviously, but you treat x as anything in that given domain, and you take your limit just like you did in like 117, right? So it's the standard limit of sequences, right? So what happens when n gets big, right? Does it go to 0? If so, pointwise. If not, not pointwise. Right? This can also identify bad points, right? You can say it goes to 0 unless x is 7. So you can say pointwise converges everywhere but 7. Right? So there's a thing called almost everywhere pointwise convergence. But not getting into that. Uniform convergence. What do? You take fn minus f. Okay, you go compute its maximum over a and b. Now, generally the maximum would get replaced with a thing called the supremum, which is it's kind of like a maximum. It's what's called the least upper bound. But yeah, sometimes these functions aren't continuous, right? And if they're not continuous, you're not guaranteed to have a maximum, right? And some other weird things can happen too, right? So nevertheless, you find the biggest of this guy, you take the limit, see if it goes to 0. Yeah. And what we end up doing here with all these things is we convert this big like question about like what happens with this sum of functions, and we're really turning it into a sum of very particular numbers, right, by doing a computation. So here I'm taking this, and that's the thing I'm asking about, right? I'm asking about this kind of thing. Does it behave well? And that's just a number, right? This, for any given value of x, is just a number. This is just a number. So we're converting between new fancy thing and old thing you like, and did I put it here? I thought I did. And the formal connection between the series and sequences is that I could say let fn be the sum from I is equal to 1 to n of fi of x, right? Now my sum becomes a sequence. So that's the connection there. Okay, let's finish this thing. So, determine if the sequence of functions defined by this converges in the L2 norm, pointwise or uniform, and if it converges, what's the limiting functions? Spoiler alert. What we're going to do is we're going to check pointwise convergence, and if it converges in these two guys, kind of thing, then for the types of functions we will see, it'll also converge to the pointwise limit, right? There are edge cases where that's not true, but for the purpose of this course, it works. So now, if I give you something like this, the first thing you want to do is you want to think, what does the function look like? And I'm going to pause and fix the typo in the question. So this is the intended function. So we're going to ask, what does the function look like, right? So if I plot this, fn, it's 0 else. So if I'm less than 0, it's 0. Okay. And if I'm bigger than 1 over n, it's 0. Between 0 and 1 over 2n, it's 2nx. So 2nx, for any integer that I'd plug in, or positive integer that I'd plug in for n, it's going to have a positive slope. So it's going to do something like this. And this stops at 1 over 2n, which is the halfway mark. Yeah. The height of this, if I plug 1 over 2n in, the 2n's and the 2n's cancel, the height is always 1. Okay. Now if I plug 1 over 2n into this, here I get my, this term cancel, so I get a 1, so I get 2 minus 1, which is 1, which is what I wanted. And if I plug in 1 over n, the n's cancel. 2 minus 2 is 0. So it does this thing. So this is like a little triangle function, right? And if I want to ask what happens to it pointwise, I really want to ask what happens as n gets big to all the x's, right? So if x is over here, right, in this area, or if it's over here in this area, well, technically square brackets, it's 0, right? And as n gets big, 1 over n gets small, right? So this gets squeezed. So in the limit, so as n is big, right, relatively speaking, this looks like a sharp little thing here, right, where this is 1 over n. This is still 1, right? So you can, if you think about this for a bit, no matter what value of x you pick, right, there is a value of n where for that this fn function would eventually be 0 for all n bigger than the one you pick. So in particular, if I say, is it true that I can find n such that this is going to be bigger than or equal to 1 over n? Right? Well, we can solve this. Multiply by n, divide by x. We say n, if it's bigger than or equal to 1 over x, then yes. So for any x that I pick in the positive numbers, right, I can do this. All right? Eventually, if I'm standing right here, eventually this wave will pass me and I'm 0 forever, right? And if fn of x is 0 for all the values bigger than this critical threshold, well, then it just stays 0, right? So the limit would go to 0, right? The one concern you could have is what happens right near the origin, right? Well, at 0, I'm 0, and if I'm away from 0, no matter how close I am, right, there will be this little area where eventually I get past and I stay 0. So here, the pointwise limit, I'm going to call it f of x, is going to be 0, right? Now, I'm not going to ask you to do a formal proof for these. I'm just going to ask you for the idea. But here's how the formal proof works. I will write it down so I can give my voice a break for a bit and still make progress making video. Okay, so if I give you an x in the real numbers, if I give you a real value n such that this is true, and you can always find the value, right? We showed here, you can always find there's no maximum for integers. We proved it in 108. So you can always find that. Then once I reach that threshold, this is always 0. So if I want the limit as n goes to infinity of f of m of x, for that x will hit 0, right? Now this is only for the positive side, right? If this is true, then we just have literally fn of x is 0, right? Because we're in the else case. We're over here. Okay, that's the idea here. For uniform, what we want to do is look at the maximum. Here, this is the maximum. The maximum is always 1. We define the function in such a way that the maximum stays at 1. So it can't converge uniformly, right? Because the error between the sequence of functions in the pointwise limit is always, the maximum error is always 1, so it breaks. Now this will converge in the L2 norm. This one, you can one way to think about it is you can ask like, hey, what's the area of this thing doing, right? Does it go to 0 sufficiently fast that the L2 norm goes to 0? L2 norm being this guy here. Well, not strictly, but the one we're using for this course. So you can get an idea of whether or not it should, right? But to formally do it, what you want to just sit down and do is do the computation. Now here, my function is piecewise defined, so if I use the piecewise definition of the function, I get this. Yep. These are evaluatable. When you do that, you get this. And then if you ask, what's the limit of, I'm going to write it like this, fn of x minus 0, 2. This is basically that. Here, this is going to be the limit. This guy just goes to 0. Right? So it would converge in the mean. So. Okay. So again, like here we're using a slight different definition of the norm just because we're not doing enough with the norm that it matters for the purpose of this course. Okay? So that's the idea, right? Yeah, do your pointwise limit, you see what happens. You go check your uniform limit, you see what happens, and then you go from there. Right? Now there are things that behave really weirdly, right? Like if I change the function, instead of going up to 1, say if this is 1 over n, this is my 1 over 2n, say I went all the way up to the value n. Right? In this case, for big N, this would look like really high up, really low down, right? Now the idea is the area of this little triangle is going to be n times, so the height times the width, so 1 over n, and a half, because it's a triangle, right? So this always comes out to be a half, right? So this still has the thing where this would slide over, so it would converge pointwise. It wouldn't converge uniform, but this area, these kind of things, can cause issues with the convergence of the L2 norm, right? So if you set these kind of problems up, you're not guaranteed things could behave in some contexts. So to illustrate this, I'm going to do the circle thing. This one's kind of fun. So if I give you a circle, it has a radius 1. Just call it 1. Here I can ask what is, just leave that alone. Here I can ask what is the perimeter? Well, the perimeter of this would be 2 pi. Now the ancient Greeks really liked approximating things with other geometric objects. So if you look closely, you can see, well, the circle and a square kind of synergize well together. So I could have tried to approximate the circle by picking various geometric objects that I know how to compute the perimeters of, and I can try to approximate the perimeter of the circle. Well, here, all these lengths would be length of 1, so this would be 2, 4, 6, 8. So pi is approximately 8. Right? Now what we can do is we can build a different structure, right? So you might go like, oh, we could use a pentagon, yada, 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 and that would be the correct option. But you can also go, I like squares, right? Why don't I just like make the square touch the circle more often? That surely gets me a better approximation. So I could do something like, well, okay, I'm going to pick a point here, and instead of doing full square around, I'm going to make the square go down here and across here. Right? So you can see that this circle looks closer to the square now. And I can ask the question, what's the perimeter of this new shape? Right? Well, what I did is I removed this part, which had a length of 1, but I added this one, or not a length of 1, a length of x, but I added this one, and I removed this which had a length of y, and I added y back. So the perimeter of the new shape is still 8. Right? But what I can do is I can build a whole sequence of these. I can pick all the points, right? So I can pick like a bunch of points here, and I'm going to make the square thing fit the circle at all these points. So it's going to go down, up, down, up, down, up, down, up, down, up, down. Yeah, pretend it's tangent to it, right? Now you see here, that looks pretty good, right? It looks like it's matching the circle really well, but this argument over here with the area I cut away was added back in still holds, right? For each one of these terms. So the perimeter of this weird shape is still 8, right? So here we have pointwise convergence. If I were to continue this process forever, right, build an infinite sequence there, you could build pointwise convergence because the points here are going to get close eventually, and you can use some arguments about density of rational numbers in the irrational numbers, yada, 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 depending on how you choose to do your construction. Nevertheless, but you can build a sequence here that does converge pointwise to the circle, right? But because it has these little wiggles all the way down, even though it converges pointwise, it doesn't converge in the mean for this case. Right? So here we'd be talking about the integral for the arc length. So you do your like square root of 1 plus f of x squared kind of thing. Plus or minus, I think it's plus dx. It's been a while since I did this, right? So you do your parameterization, integrate over this, right? And then you just don't get nice convergence in terms of the area, which is the analog of the mean, right? So yeah, you're not necessarily guaranteed that things behave well there. So that's just something to be aware of. I'm not going to test you on this kind of thing, but it gets dangerous when you start swapping the orders of limits and integration, and we will have a little bit of that to discuss later, but we'll do it in the context of Fourier, which for the functions we work with won't be horrible. Okay, so that is it. If you had questions on some of these, ask. Again, this will be on homework, but I won't put it on the final. It's fair to test you on it, but I just want to make the focus Fourier because that's really what you need out of this material. And the purpose of doing this is so that you can go understand this. Or not that one. So that you can go understand this, right? Fourier converges to the mean and this on finite subintervals, yada, 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 right? This is actually useful. The proof technically isn't beyond the scope of the class, but it's just tedious, and I don't want to get into all the details. But what that lets you do is it lets you talk about how the Fourier series acts as an approximation of the function. Yeah, it's quite useful there. Okay, so we're going to stop here, and I'm going to stop talking.